Welcome back to Sensei Security School. Today let's learn how to do a stack overflow. Next 15 minutes we're going to take a look at how to actually exploit a vulnerable binary and launch a shell to run whatever commands we want. We have a sample target here. I've opened it in a UI called Cutter. That includes a decompiler called Deirdre, so we can see what the program does. But in this particular case, we actually happen to have the original source, so we can look at it in this format. If you didn't have the original source, you could use a decompiler like Deirdre. Let's take a look at what this program does. Looking at main, it gets our user ID, okay, checks to see that we passed an argument. The name of the program is the first argument, and then the user must pass the second argument. Let's see, it strips the environment, it says. And then, it passes our argument to this function called start. Let's see what start does. Start copies the argument called string copy to copy it in this buffer. You may know string copy is actually a vulnerable, dangerous function. This is something that's going to allow us to hack this program. The reason for that is we don't see any link here. String copy is going to copy the source, whatever data we pass it, into this fixed length buffer that's 0x100 bytes long. I believe that's 256 bytes, without checking the length. So it could write past the buffer. Let's say we were write, 1,000 bytes. It's going to write more than the buffer and overwrite memory at whatever place. Let's see what kind of memory we might be able to overwrite and see what that looks like. And what does it have to do with a stack anyway? If we open this target program in the GDB debugger, we can take a look at the stack, the memory, and see what exactly happens here. We'll put a breakpoint on the start function because that's the one we're interested in. And let's run it with the argument Sensei teaches. This is using the PETA plugin to GDB. It shows some useful information. It shows the assembly code of where we are here in this start function. And it shows something it calls the stack. What the stack is, it's simply an area of memory used by a function. The function uses this area of memory to store local variables, arguments passed to the function, and certain other things. And in fact, if we look here on the stack, we can see our argument that we passed to the function, Sensei teaches. Right before the argument, Sensei teaches, we see this kind of a pseudo argument. It says main plus 193. And that's very important. What that is, at the end of the function, of course, a function returns. Right? It goes back to wherever it was executing from, in this case, main. The function needs to know where to return to. Where should execution go after the function finishes? And that's what this kind of pseudo argument here is. The return stack pointer says to the function, when you're done executing, send execution back to this location. So that's going to be important here in just a little while. You see that is currently located at D188. Let's step through this function here. We see the next thing it's going to do, it's going to subtract sub from the ESP, from the stack pointer, 0x100. What that's doing is it's subtracting from the address of the stack pointer in order to make room for our 256 byte buffer. We'll step through the next little bit of assembly code here until it gets ready to call string copy. Just before it calls string copy, we see the arguments being passed to the string copy function are our input, Sensei teaches, and this other argument is actually the buffer that it's going to copy into. Let's take a look at what it looks like after it's been copied into the buffer. Now we see the stack has 2 copies. So string copy did its thing and copied our input into this buffer. We step forward a little bit more. What we're going to step toward is this instruction called ret, R-E-T. That stands for return. That's where when the function returns back to where it was called from. And just before we return, we can see on the top of the stack, this first item is in fact main plus 193. So it's going to return back to the main function at offset 193. And it should be this address, this 8645 address. And sure enough, that's where we are. We're back in main. Here's the address that we saw. And that's how this program is supposed to work. What if we did something different? What if we passed more than 256 bytes? Let's see what that would look like. Now I have a Python script to call the function from in our debugger. Just because using a Python script, it makes it easier to know exactly what we did and make little changes and refine to get exactly the right arguments that we need to exploit it. Here, this is going to generate a input string, an argument that is OX 110 bytes long, it's longer than the buffer. And then we're going to pass that, call GDB on the target with that argument, with that payload. Let's take a look at what that does. It opens our GDB debugger because I asked it to do that in the Python script. It set the breakpoint at start, so we'll continue to that breakpoint. We are in start, and this is our input. It's this interesting pattern of A, AAA, B, AAA, C, AAA, D, AAA. That's the pattern that's created by that cyclic function that I used. In a moment, we'll see why that pattern is useful. If we just go ahead and step through this until we get to the return, we'll go past our string copy here. We see when we call string copy, indeed we have more than one copy of this patterned input. And here at the return instruction, if we look at the top of the stack, this should be where we're going to return to. But instead of something that looks like main plus 193, instead we have QAAAC, RAAAC. This is part of the pattern that we input. So what we've done here is by writing 110 hex bytes, we've written past the buffer and overwritten our return value. So let's see what happens when we try to return. When we run that return instruction, it says invalid address. It's trying to return to this QBack rather than to code. Yeah. So we've successfully overwritten the return, and we've hacked the program to cause it to try to execute code that it's not supposed to execute. Now let's be a little bit more careful. Instead of just doing an interesting pattern, maybe we can make it execute code that we're interested in. For example, maybe let's say this were a login program, we could have it, we'd give it the address of the login approved function. Any function in the program we might want to call. What it tried to call here, it says, is this 63, 61, 61, 71. So that's what got overwritten onto that return address. That kind of tells us how long how far into the input ended up to that point. So what we can do is just make a input that's exactly that long, that's long enough to be able to find, to be able to create that particular value. And the cyclic will actually stop right before creating that one. And then we'll add this OX deadbeef to our input. And if we get it right, if we calculate it right, OX deadbeef should end up being our new return pointer. So you end up overriding that return pointer. Let's take a look and see if that works. So hit return or hit continue to get into start. We see it subtracts OX100 in order to make room for the buffer it's going to copy into. We've used the next command a couple times to step through this. We see it's about to copy that. Sure enough, we have multiple copies. Getting down here closer to the return. Sure enough, here on the top of the stack is this dead beef value that we put in. And it's about to call return. And it's going to try to return to OX dead beef. See that happen. It tries to execute whatever code is at this dead beef address, doesn't find anything executable there, and complains about that. What address would we like to put in there rather than dead beef? We can get it to execute whatever memory location we want. If this program potentially did something interesting, like it was a login program, obviously we could have it go to the part of the program that we want it to run, like accepting our login. Maybe we could do something even more interesting. How could we get a shell and have it run whatever commands we'd like? Well, we can only execute code that's in memory, right? Because we're giving a memory address that says execute the code at this place in memory. What if we want to execute code that's not part of the program? Well, what's in memory? Our input. Whatever argument we give the program, that ends up in memory, doesn't it? So, what if we give it the address of our input and we tell it to execute our input, right? So we overwrite our return pointer with the address of our input. Let's give that a try. What I did here is I wrote assembly code that pops a shell. Pretty much what this assembly code does is it calls this execve system call. Prior to calling execve, it puts some arguments on the stack. In particular, it puts bin sh on the stack, bin sh. The name of the program being sh. It null terminates the string, does some kind of housekeeping tasks, and then calls the system call to execute bin sh. I'm going to build a input, a payload here. It's going to have one other thing in assembly code. It's going to have 24 no operation codes, NOP. The no operation assembly does exactly what it sounds like. It does nothing 24 times. The reason I have that there is, let's say I accidentally get the address to return to off by 4 bytes or 8 bytes or 2 bytes. That's just going to stick it right in the middle of these do-nothings. And so if I'm off by a few bytes, forward or backward, that's fine. It'll just start running some doing nothing a few times and then pop our shell. We have our cyclic input, or just generating some bytes until it generates the address that we found earlier, the address that it crashes at. And then this is the address of our input that I saw from GDB. Let's take a look and see what happens. We see that here is our input, all this OX90, that's the no operation, the do nothing assembly code. So if we put the instruction pointer anywhere in here, it's just going to do nothing a bunch of times. And then we see bin sh right here. It's actually backwards because of Indianness, right? Big Indian and little Indian. When we push this stuff on the stack, it ends up being backwards. And then we have some weird looking hex numbers. That's our assembly code for executing this bin sh. Let's see if it did it. Hey, look at that. We are now able to do anything we want. We have a shell. Because we were able to overwrite that return value by writing more input than what the buffer was expecting. So let's take another quick look at exactly what that looks like. We look at our script again. We have our assembly code for hey, run a shell, execute the bin-sh. We have our not slide, which just makes it easier. We don't have to hit our target exactly because it'll just do nothing for a few instructions before doing whatever we want it to do. I assembled this assembly code to create x86 machine code. Pad out, this is going to end up being something like 256 bytes long, right, in order to fill the buffer, and probably 4 more bytes after that, because there's another value on the stack, actually. And then the address that we want it to return to. This is actually the address of our shellcode. We pass that as the argument, and we got our shell. You might say we already have a shell in order to run the program, but consider the program you're attacking. It could be accessible over the internet as a login program, part of a website. And based on the username that you put in shellcode in the username and pop a shell and have a shell on the web server. All the way to, imagine maybe the program is part of an ATM machine and the input is on the mag stripe on the back of the card you put in. So you could actually record a mag stripe on a supposed ATM card that has shellcode input, and you pop a shell on the ATM. And at that point, you're able to tell it to, eject cash or whatever you want it to do. This code is a simple example of a buffer overflow. Modern compilers do have some defenses to protect against this simplest example. However, it's still relevant even with modern compilers. We simply add some things to get around the defenses. Compilers add a defense, the attacker adds something to get around that defense. The basic method remains applicable. Thanks again for coming today. In the comments, let me know if there's anything that's unclear, anything you'd like a video to explain more, or any topics that you would like to hear about in future videos.